All right. Hello, everyone. Welcome to the final edition of Functional World before the summer break, of course. And we are closing up the season with an exciting talk from Lee, a well-known contributor in the Scala community. And today he will guide you through Mill, Scala build tool design as a faster, simpler, and more scalable alternative to SBT. You will learn how Mill works and what makes it stand out in real-world development. And as always, feel free to drop questions and comments in the chat. Lee will answer them all during the Q&A session right after his talk. And just a quick reminder from my side about the upcoming Scala Days in Lausanne. They are coming up very soon. So if you are still considering attending and don't have your tickets, please remember that Scala can offer you a discount. All you need to do is reach out to me via LinkedIn or email, and I will be happy to help you proceed with this discount and just happy to connect with you. So that's it from me. Let's get started, Lee, if you are ready.
Okay. Hi, everyone. So my name is Haoyi, and this presentation is about better Scala builds with the Mill build tool. So the motivation of this talk is that the complexity of the standard Scala build tool, SBT, has been a long-standing pain point in the Scala ecosystem. SBT confused me when I first learned Scala in 2012, kind of hindered adoption when I tried to use Scala at my first job at Dropbox in 2014 and 15. And now in 2025, like 12, 13 years later, I still see people getting confused by SBT, and I myself still have problems whenever I need to touch an SBT project. So this presentation isn't all about SBT, but we will explore what are the challenges of using SBT that remain today, despite the progress that's been made over the past decade. Why are build tools like SBT usually so complicated? Like, why hasn't someone just made a super simple build tool and let everyone get on with their life? And lastly, we'll look at Mill, which is a newer Scala build tool that tries to improve upon many of the use cases that SBT has problems with. So things like performance, ID support, or configurability Mill tries to be much better than SBT at that, and aims to solve this long-standing problem where SBT is a pain point in the Scala ecosystem. So about myself, I've been working on open source Scala projects since about 2012. Projects like the Ammonite REPL, the Mill build tool, upickle JSON library, OSLib, file system subprocess library. Many of you in the Scala community probably use one or more of these projects. Apart from my open source work, my professional expertise is developer tools. That's what I did at Dropbox, my first job, as well as my second job at Databricks. So I've done everything from development environments, CI systems, testing systems, deployment packaging systems, build systems, and so on, and spent many years wrestling with these challenges in quite large and growing organizations. I'm the author of the book Hands-on Scala Programming. So if any of you want to learn Scala and are curious about trying to use Scala in an easy and convenient way without so much of the high-level abstractions and complexity that's common in the Scala ecosystem, Hands-on Scala Programming is a great place to start. So this talk will have 4 sections. First, we'll ask the question, can Scala builds be easier than they are today? What are the challenges of working with build systems like SBT? Why are these challenges still present in 2025, 12 years after I learned Scala and maybe 20 years after Scala itself was created? And why is it so hard to make it easier than it is today? We'll then look at section 2, which is what is the Mill build tool. Mill is a new alternative to SBT. It's one of my open source projects. And we'll look at why is Mill interesting and what are the key ideas behind Mill that make it so unique. These are the reasons why SBT and other build tools haven't been able to make progress while Mill is able to. So first, can Scala builds be easier? I think most people would agree that the biggest problem with a tool like SBT is how difficult it is to use. So SBT is powerful. It can do almost everything you want. It's flexible, and it can be very performant if used correctly. But this if used correctly caveat is quite a big problem. It isn't easy to get good performance out of SBT. It isn't easy to understand and manage your SBT build. And it isn't easy to extend SBT or configure SBT with plugins to do what you want. So although in theory SBT is everything you want, in practice it's not so simple, and SBT often falls short despite its theoretical potential. Scala CLI is a newer player on the market. Scala CLI is a great tool for small projects. Small project typically meaning like one file at least or one module at most, but isn't good for larger projects. Like any large code base, you will have multiple modules, you will have multiple test suites, you will have some dependencies between them and some shared code. So while Scala CLI is great, it isn't really a substitute for SBT that many people use in their big proprietary code bases today. So going through these problems, like maybe case by case, just running SBT has a lot of subtlety to it. Like you need to open SBT shell, you need to make sure you run things in the shell. If you get out of the shell, you need to go back in the shell. If you need to update your config, you need to reload the shell. Just think like what other command line tool do you use that requires you to open a tool-specific shell? There aren't many of them, right? Like there's maybe one or two like GDB or PDB or others, but the vast majority of command line tools don't make you do this. And SBT does make you do it. And as a result, it's just another thing you have to juggle along with your build code, along with your application code, along with your test code, along with your product requirements. You have to manage your SBT shell just to run your program. Another thing that I personally hit more recently is parallelizing tests in SBT. So there are many flags related to test parallelism in SBT, like there's 6 of them, 5 of them listed on the right, and they interact in quite subtle ways. For example, parallel execution usually works, but if you set fork in test equals true, then parallel execution no longer works, and you need test fork parallel. And not only do you need test fork parallel, you might need to modify the concurrency restrictions, but not the normal test concurrency restrictions, but test fork group concurrency restrictions. And if you use test grouping, that may make your tests faster or may make your tests slower depending on the details of your exact test suite. So last time I needed to parallelize a test suite in a SBT build, which was maybe a few months ago, I took 2 hours and I ended up having to ask for help on Discord, and someone came and rescued me because I just couldn't for the life of me figure out how to parallelize my damn tests. The next thing I'm going to mention is IDE support. So SBT is written in Scala, and it does have IDE support both from Scala as well as built in for SBT, the tool specifically. In IntelliJ, VS Code, it all works, but there are a lot of limitations that it doesn't work as well as you would like. So over here, I have the Gatling code base open in my IntelliJ IDE. Gatling is an open source load testing framework written in Scala. They recently started a startup around it, trying to commercialize, and it's a big Scala code base that can put a lot of load on your HTTP or other network servers in order to measure their performance and see how they misbehave or don't misbehave under load. So Gatling is a big Scala project. It's built using SBT, and I have the SBT build open here in my editor. So the first thing you'll notice is that there is IDE support for SBT in IntelliJ. You can, for example, jump to like some of these keys. Let's see, I can jump to the Gatling module, it goes to a useful place. I can jump to code analysis or settings, it goes to a useful place. And I can jump to some other places. But in other cases, the jump to definitions doesn't work as well as you'd like. For example, if I jump to library dependencies, it brings me to this like stub. And in theory, I could download the sources, but even if I download the sources, all I get is a stub and it tells me the type signature, which is a sequence of module IDs for library dependencies, but doesn't tell me anything else about this. So this is not a problem if you've already memorized the SBT handbook and documentation and know what all these tasks do. And this is not a problem if all the tasks have perfect documentation strings telling you exactly how to use them. But you all know that in practice in large code bases, that's not the case, and SBT is no exception. In a large code base, for example, the Gatling application code base, you may open up any file in this code base. For example, I'm just going to pick one at random. Let's say I open up expiry support. You see this object has no documentation, there's no Scala doc, but nevertheless, you can find your way around it just by jumping around. Like if you don't know what clock is, you can jump to clock. If you don't know what system.current time millis is, you can jump to system.current time millis, even though it's in the upstream library. And by just jumping around your code base, you never get stuck like you would trying to jump around SBT. In SBT, some things you can jump to, and many things just jump to this decompiled bytecode with these stubs telling you the type signature and nothing else about the project, about the key that you're looking at. Like it doesn't tell you what value is there before, how it got computed, doesn't tell you what upstream tasks it depends on, doesn't tell you what downstream tasks use these values. It's just a type signature, that's all. And you may wonder, like, if SBT is Scala and the Gatling code bases we saw earlier is in Scala, and I have them both open in IntelliJ. Why is the IDE experience so different between the two? And the answer is, the problem with SBT is that it's really just a wrapper of global mutable variables. Like the one case that you jump to definition in a Scala code base and find nothing useful is when you jump to a global mutable variable, you get a type signature, you get equals null or something similar, and you have no idea where the data came from because anywhere in the whole world could be reading and writing this global mutable variable. And that's the same case with SBT. Like, we don't know who's writing this spotless value. We don't know who's reading the spotless value. And as a result, both humans and IDEs have problems navigating code in SBT that uses these global mutable variables. And just because we wrap them in this type-safe DSL doesn't make the values any less global or any less mutable. And we don't use global mutable variables in application code precisely because it causes problems with humans and IDEs. But build tools like SBT, and not only SBT, build others like Gradle or Maven or others, all suffer from this problem that makes them very hard for toolings like IDE to analyze. So that's the problem with IDE support. In theory, it should work. SBT is Scala, it has a great IDE support in Scala for IntelliJ, but in practice, the use of global variables causes problems. The last thing I'm going to touch on is the problems with extensibility. So on one angle is that SBT has a lot of plugins. That is good in that you can usually find the SBT plugin to do exactly what you want. On the other hand, that is bad because SBT needs a lot of plugins to do anything. Even basic things like building an assembly jar, you need a plugin, or running JUnit 5 tests. That's the most popular testing framework in the entire JVM ecosystem. You need a plugin. And so what ends up happening is you end up gathering this collection of plugins of varying quality, in this case maintained literally by 9 different organizations, and you don't know who these guys are. These plugins may be broken, they may be out of date. You copy paste them between projects, they may interact badly between each other. Upgrading them may be a problem because when you upgrade them, they may break or the behavior may change. And when you set up a new project, either you copy paste existing projects half-maintained plugin list, or you go on like a grand tour of the Scala open source ecosystem to assemble your Avengers team of plugins to do things like auto-formatting or running your unit tests or making an assembly or Graal image. So that makes things more complicated. And although SBT can in theory have plugins that does everything that everyone wants, in practice, assembling and even worse, maintaining this list of plugins can be difficult. And then there comes a case where the plugins are not enough and you need to customize the build yourself, either by writing code in the build in case of SBT or writing a plugin that you use in your own build. This happens a lot in any real project. You may need a custom bill of materials for security scanning. You may need a custom linter that one team in your company wants to use, but other teams have not wanted to adopt yet. You may want some Git metadata put in production so the application code servers can serve the Git SHA that they'll deploy that, so you debug problems in production by tracing production list behaviors back to the commit that they began at. So there are many cases where you want these custom things, and you may not always find the plugin that does exactly what you want. For the case of this example, I'm going to use this as an example. I want to count the lines of code in a project and save it as a line count txt file for use at runtime. So this is kind of arbitrary and synthetic, but it's representative of the many arbitrary things you may want to do in a real project. So this can be done using SBT, but it's not trivial. It's not impossible. Here, the example code's in front of you. But when you actually look at it, the build logic that I actually want to implement is trivial. So the requirement on the top left is so easy that I expect any new grad or even student to be able to implement it in maybe 60 seconds without any errors and without any documentation. And the actual build logic embedded in this SBT code is similarly easy, literally like maybe 10, 20 seconds of typing with autocomplete to fill out all this and type out some Scala doc or SBT documentation strings. But getting all the other stuff wired up, that's where the tricky part happens. Like when you use def task and task value versus just using a normal like curly brace block. Do I need compile in here or can I leave that out? Do I need compile as part of the line count as well? Should I be using this build or global here, or should I not be using those? And all of these things have answers, and all of these things have reasonable answers. But the point is that it's so much trickier than you'd expect such a trivial requirement to be. The trivial requirement should have trivial code, and here we do see trivial code, but it's surrounded by this other non-trivial SBT stuff that can be very easy to get wrong. And that's why many people always want to avoid putting logic in the build system because it's so easy to screw up this seemingly arbitrarily unrelated wiring you need to do to wire up the actual build logic you want to do. And that's not even unique to SBT. That's the case with Gradle. That's the case with Maven when you're using Maven exec and you have to use a bash script. It's so hard for these build tools to be extended with custom logic, even when the custom logic is as easy as it is here. And for any real world extension that ends up being a bit more complicated, the complexity just goes through the roof and becomes unmanageable. So these are the three main problems we see with SBT. It's all about the ease of use, really. The performance could be good, but it's so easy to screw up and have a slow experience to command line. And it's so easy to just not parallelize a test because getting them parallelized is so tricky and troublesome. I mean, I had asked for help on Discord. I'm sure many of you out there couldn't get it working and didn't bother asking for help and just suffer your slow tests every day because you're running on one core of the 10 cores you have available on your modern laptops. The ID support, while in theory you can figure out what your build is doing in practice, is just so hard to navigate. And the extensibility story is similarly, it's just harder than it should be, even for trivial extensions. So you may ask, why are build tools so complicated? Why doesn't SBT just make everything so simple? Or what Scala CLI already makes everything so simple. Why doesn't everyone just use Scala CLI? And the answer is that build tools are complicated because they really need to do a lot of different things. And trivial tools like Scala CLI that do not do these things are simply unsuitable for larger projects. You find yourself wondering, why am I only compiling using one core on my 10-core laptop when I could be using more of them? You find yourself asking, why am I rebuilding the same thing I rebuilt 5 minutes ago, and rather than just using the cache version? And the answer is, if your SBT or other build tools do not do any of these things, you will find yourself asking these questions, having these problems, and ultimately not being unable to use those build tools, regardless of how simple they are. That's why tools like Scala CLI cannot just take over the entire Scala ecosystem, despite their simplicity. People need this stuff, and because people need this stuff, and it's not so easy to simplify. You can imagine that if I define a class that models all these things, or I define a set of classes or an interface or a trait in Scala that models all of these concerns, it will be quite a complicated class. And that's why build tools like SBT and others like Gradle or Maven or Bazel end up being very complicated pieces of software. So that's the kind of the top level, first section of this talk. Can Scala builds be easier? We hope so. There are lots of areas where we think it's not as good as it should be, but it's not so easy to simplify because build tools really are that hard. So next we look at the Mill build tool, which is an open source project of mine that tries to make progress here where other build tools have struggled with. So Mill is an open source JVM build tool. It's been around for 8 years now, so it's not a new project. Although it originally targeted the Scala ecosystem, now it also supports Java and Kotlin projects. It mostly does the same things as the other build tools, but aims to be faster, easier to use, and easier to extend. One interesting top-level metric is now that it supports Java and Kotlin, we have benchmarked Mill to be 3 to 5 times faster than Maven or Gradle for building the equivalent Java code within the equivalent project structure. So even if you're not using Scala for work, if you're using Java, Kotlin, you also can check out Mill and see whether Mill's Java, Mill's Kotlin support is useful to you. Mill is not it's not the dominant build tool in Scala, but it's not small. I think it's used by many of the newer projects. Projects like Corsair, which everyone uses for dependency resolution, are built using Mill. Scala CLI, which you all know is not built using Scala CLI. It is instead built using Mill. The hardware chip design part of the Scala ecosystem is built using Mill, as are all of my own projects. So Ammonite, OS, FastPass, UPickle, they've all been built using Mill for maybe 5 to 10 years now, 5 to 7 years now. So Mill is very much production ready, even though it's not the biggest build tool out there, and can be used outside of Scala as well if you are not using Scala in your day-to-day work these days. A basic Mill build looks like this. I have a package declaration, imports, object foo extend Scala module. That means that my foo subfolder has Scala code in it. I need to define methods to configure it. For example, I override Scala version, override my Ivy dependencies, with, in this case, HTML rendering and argument parsing. I have a nested test suite, foo.test, that has its own configuration for dependencies and a test framework configured. So you can compile foo.run to run, foo.test to test, foo.assembly, and use show to print out the path and run the assembly later. These are all just basic build tool things. So far, nothing special. The next example is an example HTTP4S web application built using Mill. And I can show you this one live. Let me pull this up. So I'm going to put this away and put in a new editor over here. So this is what we saw on the slide. It's a HTTP4S web app. I can do, for example, mil test to run the unit tests of the web application from the terminal. Let me see, in this case, I just have one test that passes. I can do mil watch run background, and this will run the web app in the background and automatically reload when code changes. So now if I go localhost 8084, this is my web app running HTTP4S. I can make changes. For example, if I change some of the HTML templates, I may change, let's say I change to-dos to hello. When I save it, you see it gets picked up instantly, recompiles, restarts the web app. Web app may take a moment to restart, as web apps do, and now I have hello. So this also works for other frameworks like Spring Boot, like Micronaut, like Kotlin's Ktor, and so on. So you can use mil for all these real projects. So people often ask, like, what does mil support? And mil in general supports a lot of the open source JVM ecosystem, both Scala as well as Java, as well as Kotlin. So all your packaging formats, including ground native images and assembly jars and JLink, JPackage, and Docker, all your test frameworks, all your languages and the platforms on those languages. So things like Scala.js, Scala Native, Kotlin.js, Spark, Android, Kotlin Android, and so on. Publishing to Maven Central, all the different linting frameworks. I have the ones for Scala listed here, but a similar list exists for Java and for Kotlin, all supported by mil. So in general, mil won't have your support for your own internal customizations because those are internal. Mil doesn't know about them. But most of the open source stuff, mil does support. And you can get quite far just with the built-ins with mil without having to go hunt for plugins, like I mentioned earlier. So that's a quick lightning tour of the mil build tool. So far, nothing so interesting. We showed all the same things that other build tools can do, mil can also do. So why do you care about mil, or why do I care about mil? And that's the next section. Why is mil interesting? I think the bottom line is that mil just solves many of the long-standing problems that other build tools like SBT or even Maven and Gradle have really struggled with for the last decade or more. Things like performance, ID support, and extensibility. Like that. When's the last time that SBT's ID support got better, you may ask yourself, and may have been a decade ago. It's very hard to improve these things, and mil has made progress, which I'll show you now. So in terms of performance, to benchmark this, we took the Gatling code base we saw earlier. Gatling is normally built using SBT, and as a proof of concept, we ported it to mil. Now, we didn't merge this into upstream because they are using their own tool, and this is just for our own experimentation, but we got all tests passing in both mil and SBT. And Gatling is quite a substantial project. So 80K lines of code, 20 sub-projects. It's not small, and it took only about a day or so to port it from SBT to mil and get everything working. Once we got it ported, we ran benchmarks on a lot of common workflows. And the first thing you notice with these benchmarks is that SBT really has two different performance profiles, whether you use it like any other command line tool naively, or whether you use it correctly, which involves opening the shell, running reload, restarting the shell, and so on. If you use it naively, it's terribly slow. If you use it correctly, it's very fast. In fact, if you benchmark, it's faster than Maven or Gradle for compiling Java, Scala, or Kotlin. But it's just annoying to have to manage this shell. And it's something that you think that the project or the software is good at doing annoying, tedious work, and the software should do it for you, or the computer should do it for you. And that's basically what mil does. So if used perfectly, mil is not faster at compiling Scala than SBT is. Mil uses the same Scala compiler, same JVM as SBT would use, same Java compiler, and so on. But mil just automates the busy work of managing a long-lived process. When you run mil from the command line, it spawns a long-lived daemon in the background. The configuration changes, mil will update the config in the daemon. If the daemon dies, for whatever reason, you Control-C and kill it, or out of memory, or crashes, or whatever, mil will restart the daemon for you next time you run something. Like, this is not rocket science, and mil just does these things for you so you can focus on your other work and not worry about why my build is running slow. Oh, I'm using SBT wrong. I have to use this other way that's taking up more of my brain power, distracting me from the work I actually want to do. Other performance optimizations that mil does are quite interesting. So for example, mil has zero config test parallelism, where it just one flag to turn on test parallelism, and generally works well even for a very wide range of performance profiles. Next version of mil will be on by default, versus compared to SBT, where it's very hard to turn it on and configure it just right to make it work for your project. Selective test execution is interesting. This is something that many code bases or projects could benefit from. So if you make a pull request, Mill lets you check out your main branch, take a snapshot, check out your pull request branch, and ask Mill what code or test suites were affected by this change in the code. And Mill can tell you exactly what test modules need to be rerun, or modules test suites need to be rerun. Mill can tell you why those test suites need to be rerun by rendering this JSON tree saying, okay, the test repo source root change, therefore test repo root change, therefore resources change, therefore test change, and needs to be rerun. And Mill can run it for you if you ask nicely. So that means that when you have a large code base, which you're often not touching the whole code base, you're often only touching small parts of it, Mill makes it very easy for you to just run the parts which are relevant to your code changes rather than running all the other tests which are irrelevant, wasting time and wasting money, which is very often the case in many projects. Mill has incremental assembly jars. So if you're making large assembly jars, for example, for Spark Submit, which is the example here, or for deploying web servers and so on, making a large 200 megabyte Spark Submit assembly jar takes time, like 20 or so seconds, depending on how warm your JVM is and how happy your CPU is. But updating an assembly jar can be very efficient. If you add a single new Scala file and re-implement and rebuild the assembly, Mill can rebuild it in 1 second rather than 20 seconds, whereas most other build tools need to take a whole new 20 seconds. That's because assembly jars are just zips, and zips are very easy to efficiently take files out of and put new files in. So this is provided by built-in as a JVM's Java NIO zip file system or jar file system. So rather than rebuilding the whole thing from scratch, Mill just takes the same assembly jar, takes out the files it doesn't want, puts in the new files it does want, and you're good to go without having to rebuild the whole thing. This can really speed up iteration on when you're working with assembly jars, which tend to be pretty large and slow to build the first time. The last thing worth mentioning is a Chrome profile. So why is my build slow is the most common question that anyone in the world has asked of their build tool. And often the answer is out there, but it's not so easy to get. And Mill makes it very easy. And let me show this to you live. So if I go to my Mill port of the Gatling code base and I run mill clean and mill wildcard.compile all, let me open this code base in my IDE. So you can see Mill, like SBT and Gradle and all build tools, is a nice command line interface telling you like what's being run at any point in time. But just eyeballing this is not always easy to see exactly where my time is going. It changes over time. You forgot what was run earlier, and so on. So what Mill does do is it provides this Mill Chrome profile JSON file, which is a standard format supported by the Chrome team at Google that has a list of names, a list of timestamps where task started, a list of durations, how long each task took, and a list of thread IDs, which thread was running my task. So eyeballing this Mill Chrome profile is not really feasible. But what you can do is you can load it into any Chrome browser's Chrome /tracing UI. So most of you probably do not know, but all of you have Chrome installed, and all of you have Chrome tracing on your laptop already. And you can just dump this Chrome profile file into Chrome tracing and get the interactive explorable view of why my build is slow. So earlier, compiling the whole Gatling code base took 30-something seconds. Obvious question, why did it take 30-something seconds and what can I do with it? And by opening this up in Chrome, I can immediately see where the bottlenecks are. For example, at first, I can see it's quite well utilizing all my cores, resolving dependencies from Maven Central. Then it gets bottlenecked on core components using 1 core out of 10. After core compile finishes, a bunch of other things kick off, including core test. And again, it gets bottlenecked on core test until that finishes, and a bunch of other stuff kicks off after that. And even if you know nothing about Gatling, even if you know nothing about Mill, you may already have ideas of like what could be improved if I want to speed this up. Do I really need to wait for the whole core test suite to compile before I can start compiling my HTTP tests? Or do they only need to depend on some shared test utils I can extract into a separate module? These test utils would compile much faster, and after they finish early on, core tests as well as Gatling HTTP tests can start compiling much earlier than they do now, shifting all this to my left, making better use of my cores, and shortening the wall clock time it takes to finish my compilation. So this is something that all build tools can give you. Gradle, if you go pay Gradle Enterprise, Gradle Inc. for Gradle Enterprise license, set up a Gradle Enterprise self-hosted build scan server and upload build scans, Gradle can give a UI for you to visualize your build timings as well. SBT, Maven all have some plugins you can probably find on GitHub and probably integrate and probably configure and call to get some kind of idea of where your time is going. But it's so much more difficult with these other build tools, you're probably not going to do it. Whereas with SVT, any command you run, running test, running compile, running packaging or publishing, even if your build is stuck and the command hasn't finished running yet, you can take the half completed JSON file, dump into Chrome, and see exactly where your time is going in your build. And that means that rather than you being at the mercy of build, taking however long it wants to do whatever it wants to do, your build, now you are in control and you can decide what is your build doing and what can you do to make things better. So that's the performance angle here. And I think the bottom line is that none of these things I showed you are impossible. You can set up selective testing based on your pull request diff using SVT. It may live in a separate Python scripts that will kind of run git diff and model the graph and decide what SVT test commands to run for you. That's how it works in many code bases, for example, in open source Apache Spark. But most projects aren't going to bother, and most projects will just suffer with slow builds or slow tests. Whereas in Mill, it makes it so easy to speed up your tests, speed up your get fast compilation, and figure out where your build time is going, that you actually will benefit from the faster performance because it's so easy to get. The next thing I'm going to look at is the ID support. So SVT is built using Scala and Mill is built using Scala. So what's the difference here? And that's what I'm going to show you now. So on the right here, I have the Mill build for the Gatling code base. I'm going to open up on the left the SVT build for the Gatling code base. For example, I'm going to look for the core submodule of the Gatling code base on both to highlight for you. So I've highlighted the Gatling core submodule config for SVT and Mill, on SVT on the left, Mill on the right. The first thing you'll notice is that the Mill config is actually a lot more verbose than SVT. And that's something that is not that surprising. Mill is not competing at how short we can make the lines of code. And so SVT does a lot of things that make the lines of code shorter, like these fancy configuration strings that Mill spells out more explicitly as methods and identifiers, and which we think is a lot more clear despite being more verbose. The second thing you may notice is that they really all have the same information. So there's Gatling core here, there's Gatling core here, there's Gatling module here, there's Gatling module here, Gatling netutil here, netutil here, library dependencies is here and here. Just because we ported the build from SVT to Mill doesn't mean that we don't need to configure the same information for each module. And modules and Scala code bases need dependencies, internal dependencies, external dependencies, test dependencies. And so Mill needs all of these just the same as SVT does. Where things do start changing is when you start trying to look at user IDE, for example, trying to pop up documentation for library dependencies gives you nothing. If you memorize what it does or you already know from 10 years experience in Scala, that's great. If you're new or maybe you're trying to look at some other task that's not so well documented, maybe you're trying to look at what a Gatling OSS plugin does, and you don't see anything, that's not so great. So in Mill, you'll find that it's a lot more transparent to your IDE. I can ask for documentation and I can get it. IV dependencies is equivalent of library dependencies in SVT. So any IV dependencies you want to add to this module, including the format for Java and Scala dependencies in the comment here. While in SVT, you jump to Gatling module, you jump to Kotlin plugin, other things, you go nowhere. In Mill, you jump to Gatling module, you jump to SVT module, you can see the configuration in front of you of what these modules are doing. So this really makes it a lot more transparent to what your build is doing. It's not just these opaque, global mutable variables. In SVT, you jump to library dependencies, you go nowhere. In Mill, IVDEPs is the override. IntelliJ knows how to work with overrides. It can show you where it's overridden from. For example, fork args was overridden from run module. Fork args, you can see the doc, can see the value it was before. This is something SVT doesn't show you because SVT is a global mutable variable, got set somewhere else and you don't know. And you can kind of just look to see where it gets used. For example, fork args gets used in runner. Runner gets used in run background task. Gets used in this deprecated thing we don't care about. Gets used in run fork task. Run fork task gets used in run. So just like that, we are able to trace through how our build tool is using our configuration of fork args to affect where we run our code. And again, if you memorize what everything is doing and you know how to do everything you want to do, and you never have to get confused with your build tool, this is not necessary. But when things go wrong, when the documentation is out of date, when ChatGPT gets confused and starts hallucinating, when Google can't get you any good answers, having a good ID experience is a great fallback to figure out what you're trying to do, what is it actually doing, and why is it not doing what you want. And you can inspect things with SBT from the command line. You can do that in Mill. You can look at the docs online. You can do that in Mill. What Mill gives you that's different is the ID experience is really very strong here. And you can explore your Mill build just the same as you can any application code, which is different from how it works in SBT, which you can't really get anything from your IDE. I showed you tracing downstream from your fork args to see how effects run. You can trace upstream as well. For example, final main class I see here. Let's say I don't know what this is. I can jump to it. No documentation like many other code bases you've probably seen in the wild. But I have implementation. And I have the upstream call. I can jump to that. Again, there's no documentation, but I can see it depends on this main class thing. And if this main class thing is any explicitly defined main class that's configured by the user, you can see now I have documentation, defaults to none. If it is configured, I use it. If it's not configured, I use all local main classes. I don't know what that is, I jump to it. And again, I can see that this is any main classes that discovered using class graph, which is an open source class path scanner that scans all your class files looking for public static void main string array args methods, static methods. So nothing I showed you is rocket science here. Like this is the exact same ID experience you see day to day in any Scala, Java, Kotlin code base, or even nowadays in Python and TypeScript. And the reason why Mill can do this and SBT cannot is that Mill, rather than being built around global mutable variables like SBT, which are not amenable for ID or even human analysis, Mill builds are built around methods, method calls, overrides, like we see here that IntelliJ can identify for us, and classes or traits in Scala. And IntelliJ and other tools like VS Code are very good at navigating methods, method calls, traits, classes, and overrides. And so they're very good at navigating a Mill build, even though there's no special support for Mill built into IntelliJ. So that's the ID support angle here. And so although Mill and SBT are both Scala and IntelliJ has support for Scala and IntelliJ has support for SBT, Mill's ID support for in IntelliJ and VS Code is much richer than that in SBT. You basically never get blocked by some unknown misbehavior in Mill, and you never get blocked by lack of documentation. And instead, like any other application code base, you can always use your ID to explore, navigate, and understand what your build is doing, not just what the documentation says what it should do. And when it misbehaves, you can always dig deeper and figure it out. So that's the ID support angle. Next, let's look at the extensibility angle. The first thing to talk about with Mill is that it has a lot more stuff built in than SBT. So things like assembly jars, native images with Graal, JLink JPackage, are all built in with Mill. GMH benchmarking support's built in. JUnit 5 Jupyter support's built in. Kotlin is built in. Auto formatting for all the different languages like KT format, Palantir Java format, Scala format, all built in. Mill still does have third-party plugins. For example, in this case, ScalaFix is a third-party plugin maintained by some guy at Netflix. I suppose to support the internal Mill builds they have at the Netflix code base. But in general, you can get a lot further with Mill without reaching plugins than you can with other build tools like SBT, Maven, or Gradle. Most of the common things you want to do are built in, and you can just use Mill rather than having to first assemble a plugin suite before you start working with your project. The next thing to mention is that when you do need to customize things, most build tools require extensions to be published as plugins, and Mill doesn't. You can just write code and use libraries in Mill to do what you want. And let me show you what this means live. So over here on my right, I have the code for a minimal Mill module, Scala module. You see there's not much here. This is a Scala version, nothing else. On the left, I have a terminal, which I'll bring to that code. And Mill support is similar to SBT and Maven and Gradle, other JVM build tools. Conventional over configuration, we inherit all the defaults from the Scala module trait or class. And therefore, if all the sources are default, run, compile, configurations, all the default. And the things we want to modify, we can override. So let's say I want to do what I did earlier, which is in SBT, which is count the number of lines of code in this module and add it as a resource file for use at runtime. How do I do that using Mill? Well, in Mill, custom tasks are just methods. So I just define method line count equals task. Within this method, I can call other methods. For example, I can call foo dot. I want to read the source code for line count, right? So I can look at all the different source tasks in my IDE. In this case, I want all source files, which is all individual source files fed into the Zinc compiler. I call it, and I can just start transforming it. For example, each file, I want to get the file path, you want to os.read.lines the file path, count the length of the lines, and sum them up. And that's all I need to do to define a custom task in Mill. You just define a method that calls other methods and and processes the return value to return its own return value. In this case, the sum of the line count for each file. Now I can do mill show foo.line count to see the value of my new task. This may take a moment to compile since you'll need to start the JVM and compiler. You see there's 17 lines of code in this dummy project. I can do inspect foo.line count. You see mill automatically captures things like what the method you call. It knows what input tasks are. It automatically captures a Scala doc for you. You don't need to put in the string. It automatically captures the name foo.line count and the file name and line number build.mill line 8. So this is all you need to do, like 4 or 5 lines of code if you include the comment to define a new custom task using mill. And I argue that any new grad should be able to do this. So now we have our line count task, but we haven't wired it into our resources yet. So I mentioned earlier that all the things like resources, sources, compilation are just built-in methods. You can see this in our autocomplete here. And the way you customize these built-in methods is by overriding them using object-oriented overrides. So I can just say override def resources. If you're not sure which one you want, you can ask IntelliJ. It tells you what all these different tasks are. And I can just say I want to call super resources. I want to maybe write my line count as a string to a file. In this case, I'm going to write to my task.destination folder, line count.txt. I'll explain task.destination in a moment. Oops, sorry, wrong hotkey. And I'm going to append a reference to my task destination folder to my resource path. So this is how I integrate line count into my resource path. And let's see what this means, especially this task.dest. So if I do mill show foo.resources now, you'll see that I have my original resources, which is now called super because I overrode it. And I have in my output folder, there's /foo resources.dest, which is this task.destination folder. So why do we do this? Why don't we just write to a random path on out folder like SBT or Maven or Gradle or other build tools do? Well, the answer is the file system in any build tool is really like the world's biggest global mutable variable. Anyone can read from anywhere, anyone can write to anywhere. You don't know who's reading from where and who's writing from where and who's writing to where, and you don't know who depends on who based on file system reads and writes. And generally, this becomes one big mess. It makes it very risky to try and parallelize or cache or invalidate tasks. You don't know what files to delete when a task needs to rerun. You don't know what tasks can run in parallel without stomping over each other's files. And so Mill tries to manage this by giving every task a unique destination folder. So in this case, the task is foo.resources. So that destination folder is out/foo/resources.dest. By giving every task a unique folder, this global mutable file system becomes like a local mutable file system. And by saying that you're only allowed to write to your own destination folder and only allowed to read from other upstream destination folders, the local mutable file system becomes a local immutable file system. So in this way, we kind of almost have solved the problem with the file system being this huge, messy, like global mutable state store. And instead, it's these little neatly encapsulated mutable file folders where every task can write to its own folder and return the file to other tasks to use. But you don't have any problems with concurrency or race conditions or collisions based on file system path that are very common in other build tools. Maybe like 2 build tools use the same folder on disk and then it screws up. So this is all we need to define our own, take a Scala module, have our own line count task, and have our override of resources to include the line count as resource file. And I can do /mill foo.run to show you that application code is now able to load the resource at runtime and print it out. So let's take this one step further. Let's say I want to use a third-party library in my build tool. How do I do that? In most build tools, you want to use Foo, you need a Foo plugin. And often the Foo plugin is poorly maintained. There may be multiple poorly maintained Foo plugins. You don't know which one to use. And writing your own Foo plugin and maintaining it can be quite difficult. So Mill lets you avoid using plugins entirely for many cases by just using the library directly. For example, if I want to use like Scala tags to render a HTML template for my line count instead of a text file, Mill doesn't come built in with Scala tags, so it's not a web server. So of course it shouldn't. If you try to use foo.run here, yell at you in the terminal, you can see it's already yelling at me in the IDE. But Mill makes it very easy for you to import any build level dependencies from Maven Central using this import ID syntax. So I can import commonly Haoyi Scala tags 0120, let's say, exactly the same as we saw earlier in the example. And when I reload this, you'll see that it will stop yelling at me in the IDE. You can see I can now see Scala tags in my external libraries list. I can now run my build. It's not using Scala tags yet, but it's not yelling at me anymore because Scala tags is now a valid import. And I can just start using Scala tags just like I can any library in my mill build. I can say HTML snippet equals task. Maybe I want div h1 line count and a paragraph of line count as a string. I want to render it. Again, you get full ID support here. You don't know what this is, you can jump to it. You can ask for documentation and so on. You can navigate around the Scala tags code base just like you can in your application code if you're wondering what it does. Now I can just do mill show foo.html snippet from my terminal. You'll see that it's now rendering HTML at build time. I can open up the cache files to see the HTML being rendered. Because it's foo.html snippet, the cache will be out/foo/html snippet. In this case, it's a .json file because I'm not writing any files. You can see over here I have my JSON cached on disk along with some metadata so Mill knows when to invalidate things. And now if I just substitute line count in my resources with HTML snippet, I can do mill foo.run, and my HTML pre-rendered at build time in a custom task, cached on disk as much automatically, computed in parallel automatically, and is now made available at runtime as a resource for my application code to use. So what's interesting here is that there is no mill HTML rendering plugin. There's no mill Scala tags plugin. There's no mill line count plugin or no mill exec plugin. And you don't need this. You just do the thing you want to do, for example, using standard like Scala, like OSLib file system library. Or if there's a library that you want to use that's not bundled with mill, you just import it and use a library directly. And you use it directly. It's the same library used in production, same version even you can use. You have all the same ID support, autocomplete, jump to definition, navigation, documentation pop-ups, type checking that you use in production, except now you have it in your build. So I think that's what makes Mill very interesting here, that although it has plugins for more uncommon use cases, for many scenarios, you can just code Mill to do what you want to do and get all the build tool things like caching, parallelism, or incremental validation completely for free without having to find a plugin that maybe half maintained, last updated 5 years ago on GitHub and decide what you want to do with it. So this is an example we saw live, and that's the extensibility angle, where for one, the plugins let you get started much quicker. You don't need so many plugins because Mill has stuff built in. And when you do want to customize things, you can just write the code you want to use and use libraries you want to use without having to find this like plugin APIs, plugin author, plugin maintenance, and all that before you can customize the build to do some relatively straightforward things. So that's why I think Mill is interesting. Like the performance, the ID, navigation, extensibility are just so much easier than tools like SVT or even Maven or Gradle. This is a Scala talk, so I showed the SVT example, but I'm sure if you've used Gradle, you know how Gradle performance is, you know how Gradle's ID support is no better than SVT, you know how Gradle extensibility, customization can be very confusing. So it's not the SVT problem, it's a build tool problem. And it's a build tool problem that Mill actually makes a lot of progress in improving on this and make it really easy to get good performance, good ID support, navigation, and very easy to extend your build to do exactly what you want and not what some plugin way does wants it to do. So next, let's look at the key ideas behind Mill. If all these things are so great, why don't all build tools have this? Why don't all build tools have excellent application level navigation IDEs? Why don't all build tools have trivial extensibility via code in your editor? And that's where these key ideas behind Mill come in. These are ideas that are, as far as I know, mostly unique to Mill. You won't find these ideas in most other build tools. And they are what allow Mill to be so special among what's already quite a mature and crowded build tool ecosystem. First, the idea of build graphs as pure functional programs. Most build tool steps look something like this. Do things to inputs to make outputs. In Mill, this is spelled via def and task and curly braces and parens, but it really means the same thing. And almost everything you do in a build tool looks like this. And this includes things like going over the network to Maven Central to download jars. Like, you may not know it, but unlike most other package repositories like npm or pip, Maven Central is a read-only immutable data store, append-only immutable data store. So you cannot like delete your left pad package and cause a whole Maven Central ecosystem to fail like you can in npm. And as a result, you can really treat Maven Central like an immutable data store, like immutable values, like any pure function. And things like generating files and depending on other files. Normally, if you just scribble over the file system, this becomes a big mess because you don't know who's writing where and everything collides or gets stale or gets deleted accidentally. But with Mill, because we have these destination folders, we can really treat files instead of file system rather than a global mutable file system. We get local immutable file system, making it fit very nicely within this functional paradigm where every task generates only its own files and doesn't touch the upstream files, and only reads from files upstream file that are given to it by upstream tasks, and only writes to its own destination folder and that it returns for downstream tasks to use. So basically, every task in Mill is a pure function. And this is, I think, quite a unique insight among build tools that are mostly all around like side effects on the file system and network. And if you look at the line count task, it can be written in two ways, either as a pure function, as a transformation of all source files upstream, or as a kind of imperative task that randomly reads stuff from the source folder and writes stuff to /linecount.txt. And although these both do the same thing, they're very different like consequences. Because the pure functional line count, we know where the upstream task is because we called it. We know where the output is because we return the value. That allows us to do things like parallelize or cache or schedule the tasks very safely because we know who depends on who. We know who can be run in parallel without conflicts or race conditions. We know who needs to be run serially because they depend on each other. We know if something changes, how to invalidate it because we know where the files on disk is cached. All because Mill takes care of all the file system for you. So you don't go and read and write to random places on disk in Mill. Whereas if you do this imperatively and you do read and write to random places like most build tools do, there's no way for the build tool to parallelize, cache, or schedule things safely. Like, how does the build tool know what file system, what files this task depends on, or what files it outputs the downstream task can depend on? You're not having to like look at the code, inspect the code, try and find these magic strings. Sometimes the strings will be computed, sometimes the strings will change from run to run. And generally, it's impossible for imperative side-effecting tasks or build steps for the build tool to parallelize, cache, or schedule them automatically for you. So there are two options: either run them serially, which is the default for many build tools. You don't cache them, which is the default for many build tools like SPT. Or you have some additional metadata that kind of registers the dependencies, which is what build tools like Gradle does. But so Mill, by simplifying it to pure functions, not only is the code shorter, but also lets you do all this stuff automatically and lets the user of the build tool, for example, you or me, just write the build logic, so to speak, of your build. I want to counter lines. Well, here's logic to counter lines. I don't have logic to read and write the files or write caches or invalidate caches and so on. The next idea is that pure functional programming is what makes jump to definition useful. So if you jump to global mutable variables, even global mutable variables are wrapped in setting key monad things, you get a stub that tells you nothing about where the value came from, because global mutable, anyone can read it, anyone can write it. You don't know who's the one doing it, reading, writing it, relevant to your particular question. But because Mill is built around pure functions, you jump to all source files, you go to somewhere useful. You get the definition and computation. You don't know all sources, you jump to that. You don't know sources, you jump to that. In general, because we are using pure functions, jump to definition tells you exactly how the pure function is computed, because that's the definition of the function. And you don't have all this confusion you get when jumping around global mutable variables in SPT or any other build tool like Gradle. So that's a pure functional program build graphs idea, which I think is unique to Mill. Most build tools have their build tasks or build steps as these like side effecting things that randomly scribble over the file system or reach over the network. And Mill kind of manages to tame it so that it becomes these pure functional build steps that can really aggressively cache, aggressively parallelize, and aggressively invalidate without the user having to lift a finger. The next idea we're going to look at is the idea of object-oriented build definitions. So one of the biggest challenges of any build tool is the requirement to define templated, customizable graph computations. So this may seem a bit advanced, right? But any build tool needs to do this. For example, if I have 3 Java modules, foo.bar, foo, and quux, they all have sources, they all have compile, They all have class paths. So you need some way to template these build graphs. They're not all not all exactly the same. For example, foo.bar.class path has no upstream class path, whereas foo.class path has upstream foo.bar.class path, and quirks.class path has upstream foo.class path. So you need to template them, but you also need to allow them to be customized on a case-by-case basis. We need a graph because we need some way to say what can be done in parallel, what needs to be done in what order. And lastly, we need the computation. Like, we're not just modeling graphs here. We actually need some code somewhere that says how to make a jar, how to make an assembly, how to download things from Maven Central, how to call Java C or Scala C or Zinc incremental compiler. So this is actually quite a sophisticated idea, right? Templated customizable graph computations. If I ask any of you to write a design library for templated customizable graph computations, it will be quite a complicated library, and that's why build tools tend to be quite complicated. And even if you're not having to deal with this as a build tool user because some plugin author upstream is doing it and you're just using plugins, if it's complicated, the plugin authors may screw it up. And that's how you end up with flaky plugins, slow plugins, or plugins that don't work well when combined with other plugins because they screwed up their templated customizable graph computations. So this still affects you even if you're not the one dealing with it yourself. So it turns out that everyone who's learned programming in the last 20, 30 years already knows a very standard API for defining templated customizable graph computations. And that API is called object-oriented programming. So when you define methods, that forms a graph. Methods call each other, they pass data between each other, that's a graph. The method bodies allow you to compute things based on this data and transform the data and pass it downstream, that's a computation. If you want to template the methods, you just put the methods in a class and implement it and instantiate the class multiple times. You just have 5 copies of a class, that's your templating. And to customize a class, you use overrides. So if this instance wants this method to be somewhat different, this instance wants a whole new subgraph of the methods calling each other, you just define a subclass, override the relevant methods, define new methods perhaps, and wire it up via method calls. So everyone already knows how to define templated customizable graph computations by object-oriented programming, and that's what MIL makes use of to be so simple. So when you say object foo extends Java module, this is literally an object, JVM object extending a JVM class or trait. When you have a class, you extend the class, you get all of its methods. These methods call each other and form a method call graph. In this case, I slightly simplified in the top right. So when I add a new method like line count calls all source files, or I override resources and call super resources and call line count, that's actually quite subtle, right? Like override, super, these are non-trivial concepts. But because you learned it in Java 101, you know exactly how this will affect the call graph. You know exactly how this will affect how these methods pass data between each other. And I don't need to teach you how override, super, and call and custom tasks, so you already know all this stuff. And once we have this graph, MIL can then do things like parallelize the blue and red tasks because they don't depend on each other. MIL can automatically do things like give every task a name. For example, foo.linecount has a name, foo.linecount from the terminal, has an output file, foo.linecount.json. We can give tasks to places on disk to put their files so they never collide, out foo compile.desc or out foo assembly.desc that never will collide, allowing us to avoid the global mutable file system problems prevalent in other build tools. And MIL can do invalidation for you. So if you touch the resource folder, which is now called super.resources because we overrode it, MIL just does a breadth-first search, sees the assembly needs to recompute. MIL also knows that compile and line count do not need to recompute, so they can be cached. MIL knows that when I want to recompute assembly, it knows where to delete the stuff from because the previous stuff is in a standard path on this out foo assembly.json and assembly.dest. And when it wants to reuse the compile and line count output, it also knows where to find it because it's all in the standard location. So what's interesting here is that MIL provides you all this stuff around caching, parallelism, invalidation, graph construction, and templating. But you never write code to template a graph. You never write code to parallelize things with futures or threads. You never write code to compute cache keys and read and write cache and invalidate caches for you. You just write very bog standard object-oriented code, objects, classes, method definitions, method calls, overrides, and supers. And you learned all that stuff and you know how to do that very well, and MIL just takes care of all the rest for you. So I think that's what's so interesting about this templated customizable graph computations. So that's the object-oriented build definition. So MIL, rather than coming up with a whole new API to design its graphs, use object-oriented programming that we all already know and are very familiar with. Lastly, I'm going to talk about the idea of a direct style DSL. So direct style Scala is a kind of a buzzword that's been going around recently. Like Martin Durkee talks about it. Maybe you want to write code without all these flat maps and for comprehensions everywhere, and without all these like wrapper types everywhere. And if you look at MIL versus SVT, I think you can kind of see what the difference is. They're both in Scala. They both have the same information, but the MIL code looks like the Scala code you write day to day. I have objects, classes, methods that call other methods, overrides, and supers. This looks exactly like normal Scala you write in Scala 101 or even Java 101. While SVT have all these weird like task key things and colon equals and slashes that are not the Scala you write day to day. So the problem with this really is that in SVT, what we have here is really two programs. You have the first stage program, which is Scala, like lazy vals, methods, slash is a method, colon equals is a method, and all that. You can jump to the implementation of slash in IDE. It'll show you the implementation of how the slash was defined. And all of this is great, and all of this tells you nothing about what your build is actually doing. So what your build is actually doing is in a stage 2 program, where rather than having Scala objects, methods, classes, and values, we have tasks and doc strings instead of Scala doc, and settings lists rather than traits. And instead of lexical scope and inheritance, like we have this 4-dimensional task hypermatrix thing that most people don't have 4-dimensional brains, so trying to think in 4 dimensions in SVT can be quite challenging. So although SVT is technically Scala, and you can navigate your SVT build with IntelliJ as Scala, just understanding the Scala tells you nothing about what your build actually does. IntelliJ jumping to a definition of colon equals, IntelliJ jumping to a definition of compile, IntelliJ jumping to a definition of task key is completely useless about trying to understand your build. And what you need to understand is all this stuff on the top right, which IntelliJ, which you and all your colleagues probably do not understand nearly as well. So for MIL, we take a very different approach. Rather than having 2 stages, MIL works very hard to try and cram everything into the first stage. So in MIL, your Scala doc are your doc strings. So you can't normally access a Scala doc at runtime to print them out from a command line. So MIL kind of jumps through hoops to make that possible. In MIL, your methods are your tasks. Your call graph is your build graph. Your module tree is your object tree. You reuse things via traits and inheritance. So because MIL kind of leverages all this stuff, IntelliJ already understands this. You already understand this. And so humans and IDEs are able to understand your build in MIL much better than they can understand your build in SVT, despite the fact that it's the same IDE and it's the same Scala language in both cases. So coming back to this list we saw at the start of this talk, why are build tools complicated? MIL does need to do all these things. If MIL didn't do any of these things, people would not use it, because no one wants to use a build tool without parallelism. No one wants to use a build tool without caching. No one wants to use a build tool without file system I/O or custom tasks or other things like that. But MIL is able to use the ideas you have from functional programming, from object-oriented programming, and from direct style Scala in general to answer all these questions without having to define a new custom API. Things like methods calling methods in a pure functional program answer so many of these questions about how tasks depend on each other, how they can be parallelized, how they pass data to each other, how do you define your own custom task. It's just a method. And the things that aren't answered by your pure functional methods calling methods are answered by the object-oriented nature of your SVT build or your MIL build. For example, the idea of a qualified method name, foo.compile, we leverage that not just to reference it in the code, but also to reference the task from the command line, and also to give the task somewhere on disk to put its things. The idea of like managing repetition via classes. So if you have a bunch of tasks you want to use in multiple modules, you just put them in a class or trait and reuse it. Or if you want to customize the module, use overrides to override some existing tasks to customize it just for this one module. Those are all object-oriented concepts that they're non-trivial concepts, but you are already familiar with them because you learned them 20 years ago in Java 101. And you can use them exactly the same way in MIL. So those are the key ideas behind MIL that I think are so unique. Like other build tools can try and improve the IDE support. Other build tools can try and like improve their performance or improve their extensibility story, but it always ends up being kind of subpar, complicated, and hard to use. And this idea of pure functional build graphs, object-oriented build definitions in a direct style program, I think these are unique to MIL, and that's why MIL is able to make progress where other build tools have struggled with for the last 5, 10, or even 20 years. So this is the last slide. I think the bottom line is, if you are like me and have ever thought that there should be light beyond, there is life beyond SVT. SVT is not like the final say in what a build tool can look like, or Maven, Gradle are not the final say what a build tool can look like. You should try out Mill. So Mill comes with a lot of very interesting ideas, these pure functional object-oriented direct style builds, and they're not just of academic interest. Like, these ideas translate into concrete improvements in performance, in ID support, and extensibility, which are all areas that other build tools have really struggled with for the past few years or decades. So SVT and build tools have been a big problem for Scala for the last 10, 12, 15 years, ever since I learned the language. And I think that with Mill, if you all can try it out and see if you can adopt it, this can really help us solve this long-standing problem in the Scala community. So the documentation is here if anyone wants to try it out. And that's the end of the talk. So I guess I can now take questions if there are any.
Thank you very much for the presentation. And yeah, actually, there is one question in the chat. And guys,
Sure.
you can just ask in the meantime. So
yeah. Have you thought about implementing Scala CLI notation for importing using libraries? The next version of Mill will have a comment notation. It will be slightly different from Scala CLI. The reason for that is that Scala CLI is optimized for being similar to command line flags. That is how Scala CLI is configured. And for Mill, we want to be more similar to kind of the hierarchical JSON structure that Mill builds are modeled on. So earlier I showed you that every Mill task, the output is JSON serializable. So the Mill kind of data model is fundamentally about these hierarchical JSON or YAML data structures. So the Mill version of this magic comments will be slightly different from Scala CLI, and will be using a YAML format rather than using the using directives format like Scala CLI is. Someone else said that comfort and elegance is a better argument in Mill's favor than its performance. Yeah, I think there are lots of arguments in Mill's favor. So depending what people like SVT, as I said, is very fast. Comparing SVT to Mill, if used correctly, SVT is about as performant as Mill. But it depends. Not everyone uses SVT. If you're using Gradle or if you're using Maven, Mill actually is a lot more performant than Maven or Gradle. So that's a selling point if you have a Java Kotlin project that you're wondering why is it so slow, why is my build taking so long, it might be worth trying out Mill. Any other questions? You can post them in the chat, I guess.
For now, any more questions? But we have some delays, so let's wait 2 more minutes.
Yeah, wait a few minutes, see if anything turns up.
Yeah, people are joining in the meantime to this YouTube stream, so yeah. And in the meantime, I will share a link to your LinkedIn maybe, so if anyone will have any questions, they can connect with you.
Sure.
All right, guys. So if there is no other questions, you have, just in case, you have a link to LinkedIn. So if you have, okay, there is one from LinkedIn.
Yes. Let me pull them up for you right now.
Yeah, but there is on the screen this one.
Yes, I see it.
Okay.
One moment. So here is some of the slides that I show at Java meetups, which is compared to Maven, Mill compiles about 5 times faster for the same code for clean compiles and much faster for incremental compiles. Maven doesn't have incremental compiler and has a lot more overhead launching the process than Mill does. The difference between Mill and Gradle is less stark. Mill is about 3 times faster than Gradle. So if any of you have migrated from Maven to Gradle, you probably have heard Gradle Inc. telling you that Gradle is faster than Maven. It's true. And Mill is, again, faster than Gradle. So Mill is about 5x faster than Maven, about 3x faster than Gradle. And I can show you this to you live. So let me pull up 2 terminals. Go to GitHub, Mill Talk, netty, cd.dot/netty. So if I do Maven. Okay, so I'm going to run Maven clean compile on the left. I'm going to run mil clean compile on the right. Okay, let me type it out manually. Mil clean and /mil wildcard.compile. So if you look at mil clean compile, this is a netty code base, which is about a 500,000 line Java code base. Mil takes a bit of time to compile the build initially and warm up. That's expected since the JVM program. So the first time I run this, it might be a bit slow, and we'll see. It might take about 20 seconds to compile the whole netty code base on 10 cores in parallel. Okay. Yeah, just as I said, about 20 seconds. If I run a second time, it'll take about 10 seconds. Because mil keeps the daemon running in the background and warms up, that benefits Java compilation just the same as it does for Scala or Kotlin. You see now it finishes in about 11 seconds, 12 seconds. If I run the same clean compile using Maven, we'll be sitting here for about 1 minute. So yeah, we have benchmarked for mil versus Maven Gradle. It is faster. Incremental compiles are faster, clean compiles are faster. This is generally a lot less overhead and better usage of the hot JVM to keep things fast. Eric said he tried different combinations of Gradle, Maven, SVT. You should try mil. It's great. The Comedy Haoyi ecosystem has been all built using mil for 6 years now. So it is very much production ready, including quite complicated builds. It can do basically everything anyone wants. And it is a lot easier to use than SVT, Maven, or Gradle, and more performant than the other two, Maven or Gradle. We can watch the Maven build compile while we're waiting for any more questions. I said it'll take about 50 seconds, and hopefully it should be finishing about now. 56 seconds versus 12 seconds. I've actually went and counted all the compiling however many lines of code, however many files lines. You see these at compiling source files lines. I've actually counted all of them, and they're exactly the same in mil and they're exactly the same in mil and Maven. So it's not like we're compiling fewer files or fewer modules. It's not like we're using a different compiler. It's the same Java C under the hood. Mil does a better job keeping the compiler warm and hot, and does a better job like removing the overhead of things like class loading and other things that aren't relevant to the build task that you're actually asking your build tool to do. Any other questions while we're here?
Okay. Seems no more questions. So thank you very much once again for the presentation, for your time. You have also thank you on the chat.
I saw that.
So thank you, and thank you all for joining us today, and see you next time.
Okay, thanks, Attila.